Hello, my name is Jason Chow. Welcome to NUTHOS-13. Today, I will cover the subject of prospect and the history of nuclear energy. That means I will cover quite a few technical subjects today. This is the list of all the subjects for today. And you can see this is a rather ambitious list. I will start with the nuclear safety. Then I will be talking about nuclear fuels. There are also quite a few new nuclear designs. The waste management subject is a very, very interesting subject. The issue has not been resolved yet. Fuel cycle covers quite a few technical areas, and it's very interesting technical areas. I'll be talking about space nuclear. Most interestingly, I'll cover the revised radiation dose limits. The health benefit from low dose radiation is a rather new subject. I'll be covering fusion and lattice confinement fusion. The new nuclear energy conversion presents a new energy conversion efficiencies. All came from the recent discovery of the gravitational wave, such that the black hole will reveal some new insights. Because of the time constraint, I can only touch on the highlights of these subjects. Fortunately, and please allow me to do a commercial here, I wrote a book which was published 3 months ago. The details for all these subjects you hear today is in the book. The title of the book is A Complete Perspective of Nuclear Energy. You may Google these words on the internet to see it. Jason Chow, Nuclear Energy Perspective. Listed here are the typical safety issues we have resolved all these years. We came up with issue resolutions with extensive effort of analysis and experience. And along with the licensing process, the nuclear power plant could get operated safely, continuously. The point is that nuclear safety does not come lightly. It came a long way with the extensive efforts. We can systematically say today that nuclear power is safe for good reasons. Let me discuss briefly the two major accidents. The Chernobyl accident was caused by two major factors. One, this particular reactor design was not intrinsically safe. And two, when the plant designers wrote the operating guidelines for the operator to follow, the operators at Chernobyl did not follow them. So one night, the deputy superintendent was politically motivated to expedite the experiment. He ordered to bypass the safety settings, and Chernobyl exploded. What happened at Fukushima was that Tokyo Electric Power Company did not establish a safety culture and did not believe that the tsunami-initiated station blackout could be deadly to a nuclear power plant. But their neighbor believed it could happen. The Onagawa nuclear power plant, just about 100 miles away, owned by another electric power company, the Tohoku Electric Power Company, that has established a mature safety culture, and spend a decade getting ready for a tsunami. The Fukushima site was then doomed, and the Onagawa site was saved. So I can say today, the nuclear power is safe in the Western world. Why? Because their hardware of nuclear power plants is designed and built robustly, and the system for the check and balance is very well placed. We need a solid system where the check and the balance need to coexist so that the operating procedures and the technical specifications can be religiously observed. That are nuclear power plants outside the Western world. That this is not the case. For this power plant, they could still be vulnerable to a major accident. Or just last summer, year 2021, a nuclear power plant operated during a power shortage situation, and their fuel rods in a nuclear reactor failed. By procedure, they should have shut down the plant at that time, but they did not. They still made excuses for keeping operating the plant. And I was very, very concerned. As for the new designs for the nuclear power plants of the next generation, there are new versions of high-temperature gas-cooled reactors using new fuels such as the trisol fuels, and offer advantages of great safety features and fuel economy. I personally still in favor of the fast reactors of the burner type that could consume nuclear waste quicker than they produce them. The accelerator-driven subcritical reactors are also a popular subject. Belgium, France, Japan, and China are actively pursuing it. This is a conceptual design of a prototype that has been built by Belgium and France and the European Union altogether. The ADS uses an accelerator that delivers high-energy protons and gets them into the core of a subcritical reactor. The neutrons are generated by the bombardment of the proton with the target, and the neutrons get to spread out into the core. This process can generate high-energy neutrons also continuously because plutonium is used as the fuel. A lot of nuclear waste placed in the core can get transmuted and therefore eliminated. The entire process will still be able to produce surplus energy so that an ADS can be designed as a power producer as well. The small modular reactors are a very popular subject in recent years also. Just during the last 3 years, I have seen many startup companies formed to design and market the various versions of small modular reactors. The real advantage of a small modular reactor is really financial, in the sense that it does not require a heavy upfront investment. The major components are manufactured in a modular manner, which will offer a better controlled construction schedule, and therefore much lower financial risk. I will not get into too much detail of the subject at this time. I will describe two other nuclear applications that have been discussed during the last few years. There are 60,000 cargo ships going around the world, each a carbon producer. Will these carbon producers get to be converted to a nuclear-powered vessel? We are talking about a new venture here. For this type of applications, you would need a small modular reactor. The nuclear fuels required will have to be a higher enrichment uranium for better burnup and for longer fuel cycle length. Russia and the Koreans have their eyes on this market. Another similar but different subject is the floating nuclear power plant. You'll be surprised to know that 80% of the world population live in the areas within 100 miles close to an ocean. That means a small nuclear power plant put on a boat could be pulled or tucked close to a seashore easily that supplies the electricity to many developed countries that will need electricity for their economic development. These countries could be the many African countries and the South Asian countries. They do not have to put up a heavy upfront investment to build a power plant. This type of arrangement could solve many issues related to a nuclear power plant, such as nuclear waste, spent fuels, proliferation considerations, personnel training associated with the nuclear power plant. With the readily available electricity, these countries could receive a jump start for the economy development. This is a relatively new market. Again, Korea and Russia have started the effort in these technical areas. ATF is the accident-tolerant fuel that has the cladding-covered silicates or the comparable materials so that the cladding will not interact with the steam. Therefore, no hydrogen could be produced like what happened at Fukushima, causing the explosions. NRC is reviewing the new fuel designs and should soon approve his use. RERTR is Reduced Enrichment Research and Test Reactors. During the early 1980s, this program was initiated by the US government and administered by Argonne National Lab. Because the fuels used for these reactors were 90% enriched uranium, which is weapon-grade materials, and that imposed a proliferation concern. Fortunately, this program was so successful that all the highly enriched fuel have been replaced by the low enrichment fuels. Now, many of you may wonder what we do with this highly enriched fuel then. It turns out that the highly enriched fuel could be now down blended to make a lower enriched fuel, such as 100% enrichment uranium. Idaho National Laboratory is prototyping the technology to produce the HALEU fuels. HALEU stands for high assay low enrichment fuels. The 20% enrichment fuel could be ideal for the small modular reactors Why? Because this type of a new fuel is necessary to prolong the fuel cycle length so that reactor core do not need to be refueled as frequently as the LWRs do today. The new fuels will have better fuel economy by consuming uranium more efficiently and produce less nuclear waste. You can see that all these subjects are interconnected. France has adopted MOX fuel for their power reactors. Using MOX fuels would be one of the fuel cycle options for the future, because if one of these days that the strategy of recycling spent fuel is adopted, designing a LWR with fast neutron spectrum, yes, with fast neutron spectrum, could be one of the viable options to be considered as a more effective design for better fuel economy. MOX fuels could be ideal for this approach. Nuclear waste and the fuel cycle are two closely related subjects. Each is deeply involved with many issues. All of these issues, each deserves a book to talk about it. So here I can quickly go over the highlights of some of these subjects. On the nuclear fuel cycle, some countries have adopted recycling their spent fuels. Some of them have not. The main reasons that they have not is that there was no hurry to do it, or they did not want to spend the investment in recovering plutonium for future use, which would trigger a complex management endeavors and technological challenges. The reason there was no hurry because more uranium mines had been discovered, and therefore the source of uranium is no longer a concern. The technology involved with recycling spent fuel is so complicated. Unless they had other additional objectives, they rather not to start the complex tasks now. Of course, there were other considerations such as proliferation considerations, lack of manpower, lack of expertise, and the political opposition. Therefore, some of the countries at the present time do not choose to recycle their spent fuel. But most of them still claim that they have not made up their mind yet, and they will make a final decision at a much later time. If plutonium is extracted out for its reuse, there could be proliferation concerns. Yet, plutonium is needed for fast reactors and for the accelerator-driven subcritical reactors as well. If plutonium is not extracted from spent fuel, and the spent fuel are considered as a waste that should be sent to a repository directly, there will be extra burden in the engineering work to avoid, for example, recriticality. On the subject of repository, in 1982, U.S. Congress passed the Nuclear Waste Policy Act that set the national policy on how to take care of nuclear waste in the United States. That was good. And because it says the government will take care of everything, The government will take the responsibility for all the domestic nuclear waste and will take care for their ultimate disposal. This act also allocated the necessary funding to do all the work. Also directed DOE to perform the necessary technical study for selecting the repository site. We all know by now that Yucca Mountain was selected but run into a problem. Using Yucca Mountain as the repository did not go anywhere. The nature of the problem is really political. It simply did not address the required consent from the local people. Be in democratic societies such as the United States, now looking back, it would make some sense that this had happened. The good news is that in recent months, some hope is seen on the horizon that the repository issue will be on its way back. The new key words are consent-based, which are nicely quoted by the Assistant Secretary of Nuclear Energy when she described the DOE work. And also quoted by Senator Manchin in his proposed legislation. This is a indication that nuclear waste issue is moving ahead towards some meaningful resolution, hopefully soon. What is the meaning of the word consent-based? It is basically the process for a repository site selection should also include the consent from the local residents. There have been 3 successful stories on this. The 3 successful stories are Finland, Sweden, and the waste isolation pilot plant in the United States. The repository site for these 3 places became successful because they obtained the consent from the site residents. So what happened in recent months indicates that the repository problem could get resolved and the nuclear waste could get a place to store. There are quite a few technical issues related to nuclear waste and the fuel cycle. So many complex and interesting subjects. I simply wish to have more time to talk about them today. Hopefully, in the future, I have another chance to talk about them. Purex and the Urex are the reprocessing methods to extract plutonium and uranium out of the spent fuel. These 2 methods use the nitrate acid as the base solution with different solvents at the various stages to separate uranium, plutonium, fission products, and actinides. The pyroprocessing method is a new method that relies on the principles of electrolysis to separate the different types of elements. Although the principles are the same, the base solution adopted is the molten salt, which operates at a very high temperature. This picture shows the principle of the pyroprocessing. Let me change the subject to space nuclear. I will briefly discuss the nuclear power using radioactive isotopes and the nuclear-powered propulsion. What you see here are the 4 rovers that are on Mars today. The bottom 2 are powered by a radioactive isotope, plutonium-238, The power generator is called a radioisotope thermoelectric generator, RTG. Plutonium-238 gives out alpha particle. Using several hundred thermocouples, the device could generate just about 100 watts power continuously to drive the rover to move around on Mars, as well as to send picture back to Earth continuously. I will use this slide to quickly describe the two types of nuclear propulsion. The one at the bottom is the nuclear thermal propulsion. The hydrogen gas is used as propellant. The propellant goes through a nuclear reactor. Basically, it is a small modular reactor or the comparable design. When the hydrogen gas passes through the nuclear reactor, it's get heated up very quickly. It's so quickly that this propellant volume got expanded to become a thrust, similar to a gas explosion, but it's not explosive. The top picture here is basically relying on the principle of a mini nuclear power plant. The reactor is here. You can see there is a power generation device or the electricity generator that produce the electricity along this line. The electricity will pass through the capacitors to power the capacitors that will make the propellant ionized, and the ions that going through the capacitors get accelerated very fast and get spent to the nozzle, dump outside the nozzle very quickly. That created a thrust, and that's the principle for a nuclear electric propulsion. I will briefly touch base on the fusion. Hopefully, in 5 years, the world's largest tokamak will be built, which is funded by 35 countries of $65 billion. This is the first time in history that scientists claimed that it would make the so-called energy break-even. Since this has been all over the news, so I will be very brief about it, but I will spend a few more minutes on a new subject called lattice confinement fusion, which is very interesting, that has brought a new hope for making a fusion machine. In this figure, the blue curve and the green curve represent the concept by a physicist, John Lawson, in 1950s, to illustrate under what conditions the break-even for fusion would occur, simply from energy balance. You see here the temperature of the plasma in the tokamak are along the horizontal line. Along the vertical line is the product of plasma density and fusion endurance. All these clusters here are the various fusion experiments. For example, EAST, E-A-S-T, is the Chinese experiments. K-STAR is the Korean fusion experiments. JT60SA is the Japanese experiments. Every time you hear some news about the breakthrough reported by an experiment, such that a higher temperature is achieved. And it is a breakthrough. But is it really a breakthrough? Yes, it is, in the sense that it moves further towards the break-even point. And it is worth a celebration. As for how far it is away from the break-even point, you be the judge yourself. So this figure is very useful in the sense it put all the claimed progresses in the right perspective. It can also explain why everyone has put their hope on the ITER. Hopefully it could finish within 5 years and deliver the product everybody is expected. The next phase is the prototyping exercise for commercialization, which may happen 10 or 20 years after that. Okay, let me talk about another favorite subject of mine, the lattice confinement fusion. NASA has been thinking about space travel using a small and efficient device to make nuclear power. The researchers emphasized that this was not co-fusion reported by NASA. And I agree, this was not co-fusion. The preparation of the samples used for the lattice confinement fusion may be similar to co-fusion, but the involved physics and the procedures are entirely different from fusion. Basically, the deuterium atoms are packed electrolytically on a host metal. For co-fusion, the host metal is palladium. But for the lattice confinement fusion, the host metal used was erbium or titanium. After the deuterium atoms are packed in erbium, high-energy X-ray is introduced to the experimental setup. The mechanism involved are the X-ray will cause a photon nuclear reaction first. That will split the deuterium atom into a proton and a neutron. The neutron carry high energy that could energize the nearby deuterium atoms again, which becomes capable of making a fusion with a close-by deuterium atom. This is the lattice confinement fusion. And the process has been proven that it is reproducible. The analytical work for this process has been published also. The entire phenomena can be predicted by the models. The next step is for this work to show how to design a power-producing device or a machine. I am excited about this subject because it explains why co-fusion did not work all these years. And when they did, why they happen only sporadically. I have another fascinating story to tell you. This is a story on the health benefit from low-dose radiation. I have so much to tell, so I will use a few slides to cover the entire story. Most people who are against nuclear energy mainly because they fear radiation. They fear radiation because they think radiation will cause cancer no matter how low the radiation level is. This is a wrong perception. people think that radiation will cause cancer no matter how low the radiation level is based on the extrapolation from the radiation victim of World War II and from the victim of nuclear accidents, such as the Chernobyl accident. During those accidents, high radiation doses, people did die from cancer caused by the radiation. But there is no data for the very low radiation level to tell what will happen to a human body biologically. The medical industry and radiation health professionals have adopted the concept that low radiation will still cause cancer no matter how low the level it is, as if there was no threshold at the bottom. So, I would like to tell a story, a true story on the low dose radiation and what it will do to a human body. I will today only report the scientific data without any of my personal opinion. The story started in 1980s in Taiwan. 10,000 residents in these contaminated apartment buildings were involved. In Taiwan, there were 180 such apartment buildings that were contaminated. The cause for the contamination was believed that a cobalt-60 radioactive element was somehow got mixed with the steel used to make the reinforced concrete as the building materials for these apartments. These apartments were all torn down eventually, and the government compensated for the condemned properties. The source of the contamination was the gamma ray from cobalt-60. On the average, the received accumulated dose for all these residents, covering the entire 20 years, was between 1 to 4 sieverts. All of them were medically followed and well documented. To me, this is a scientifically qualified story or study. Let me tell you how the story ended. Statistically, or medically, for 10,000 people on the average, any 10,000 people, for this case, 10,000 people in Taiwan, the cancer mortality is 232 people on the average. But for this 10,000 residents, affected, contaminated residents, only 7 die of cancer. I was very surprised to see these numbers. Medical professors and researchers, totally 14 of them, collectively published a paper on this story. This is the publication. To me, this is one unique, important, self-consistent, and scientific study that unmistakably indicates that the low-level radiation will bring some health benefits. In the United States, the National Council on Radiation Protection and the Measurements, with the DOE and several other national organizations, have participated in a study on how the radiation would affect people biologically by studying all the workers who had worked under radiation environments, it was so happened that the total number of these workers slightly exceeds 1 million. So it has been called the 1 million person study. It covers the time for the last 70 years. And this is an ongoing effort. 2 months ago, the American Academies of Sciences issued a document on revitalizing low-dose radiation research in the United States. American Nuclear Society is also playing a leading role on this low-dose radiation, which is ongoing research and education effort with the goal of closing the gap between radiation protection regulations and the state-of-the-art scientific knowledge. The main point is that the scientific communities began to realize that this subject could not be ignored because there are simply too much at stake in it to ignore it. The health benefit are at stake. I wish all the nuclear professionals and the scientific communities should keep a very, very open mind about this subject. We need to do a lot of studies to confirm the required scientific basis to identify the level of the radiation where the health benefit could be identified, and likely the regulations on the radiation dose limit should be properly revised. Most of the subjects you heard today are what I call the short-term subject. But there are other subjects that in the category of long-term prospect or of the much longer terms. The discovery of gravitational wave in recent years is an indication that black holes are working according to the way general relativity had predicted. So what's the point? The point is E equal to mc squared will be soon recognized that it needs to be updated to bring a new relationship for the mass and energy conversion. The current mass and energy conversion, either by fission or fusion, all suffered from a very low energy conversion efficiency. And the number is below 0.1%. The new mass energy conversion will have a much more energy conversion efficiency, but that is outside the scope of today's talk. Allow me to use this opportunity to share with you some sweet memory on NUTHOS. I was the technical program chair in 1984 for the very first NUTHOS conference. I had people listed here to show you those who worked with me at that time to organize the very first NUTHOS conference. I would like to thank Professor Neil Tardress, Professor Hisashi Nagata, Dr. Ibin Chen, Professor John Kim, Professor Song Hyun Cha, from the very beginning to make it a success. At that time, we had no clue, we had no idea that this meeting will turn into a meeting series. At that time, all we wanted to do was to make a world-class, top-rated international conference. That's all. But I'm delighted that it turned out to be this way. What you see here are the first 5 proceedings for the first 5 NUTHOS meetings. At that time, there was no internet, there was no CD, not any kind of electronic media, so everything had to be made hard copy. Needless to say, I am very proud to be a member of the NUTHOS team. I wish NUTHOS-14 and the future NUTHOS conference are successful, and most importantly, NUTHOS series will last forever. Today, I introduced to you quite a few technical subjects on nuclear energy. With the ongoing activities, the nuclear professionals will be busy for the next 10, 20 years. There are simply so many interesting new nuclear sciences and technology waiting to be matured or to put in good use. I'm happy for the general public as well, because that we will receive more benefit from nuclear energy ever than before. And I feel very excited. So for nuclear energy, the fun is yet to begin. Thank you very much. I will see you at the next conference.